Good evening, everybody, and welcome to the fourth HAIC Talk in our series of public lectures. It's a pleasure to see everybody here. My name is Andrew Pavid. I've been organizing this series of talks so far. For those of you who are new here, I see some new faces in the audience. A few words about HAIC briefly. The Helsinki-Aalto Center for Information Security is a joint initiative between Aalto University and the University of Helsinki, the two leading universities in Helsinki doing cybersecurity. And our aim is to ensure excellence in education and research of cybersecurity in the capital area. And so we do this in three main ways. The first is fundraising. So if we talk to your company about potential fundraising opportunities, please do come to that discussion. The second is corporate engagement. We have lots of students who are looking to engage with industry, and so we try to be a conduit to facilitate engagement between companies and students. And the third aspect is public outreach, and that's what you're here for this evening. This series of HAIC Talks that we launched in February aims to bring international experts and, very fortunately, local academics to speak about topics that are relevant and interesting in cryptography, in information security more broadly, but to a general audience. So if you don't know anything about information security, that's fine, you're in the right place. Chris will make everything clear after the talk. And so this evening we're very privileged to have Professor Chris Brzuska, a new faculty member here at Aalto, to give the lecture. So Chris's area of expertise is cryptography, and his activities range from finding numbers that look random but are apparently not random, through to very practical and applied things like secure electronic payments. Chris studied mathematics in Essen and Bordeaux and Darmstadt, and his PhD is from TU Darmstadt. He's also worked in industry, he's worked as a postdoc researcher at Tel-Aviv University and Microsoft Research, so industrial research, and as a professor of IT security analysis at TU Hamburg, where he collaborated a lot with NXP Semiconductors. And so without further ado, I'd like to welcome Chris to give this evening's HAIC Talk. Chris.
Thanks a lot. Okay, so I would like to talk about hard problems in cryptography. And I would like to explain to you what type of hard problems we're looking for. So, but before going into hard problems, let me actually ask the question, why does cryptography rely on hard problems? Why do we actually need hard problems? So, say you want to access a website, say the website of Kino Engel, and this little S in HTTPS, that stands for secure, it means that there's a subprotocol running that's securing the communication. The subprotocol is very complicated. It's over 100 pages specification. So I just simplified it a lot for this presentation. So the way this roughly works is that the server of Kino Engel sends over a trapdoor function to my device, such that the server has a trapdoor, and then I take the secret information that I want to send to the server, for example, my credit card number when I want to buy my movie tickets, and I run it through this function f. I get something something that looks very different, and I send it over to the server, and the server can use the trapdoor to invert this process that I run here and get back the secret information. And so, okay, so what do we want here? We want that if anyone listens to our communication, we want that that person will not learn anything about this secret information, for example, the credit card number that was somehow transmitted from my device to the server. And so how could one try to recover this information? So the first way to do it would be to say, okay, so let's try to find this trapdoor that the server has to recover the information. And so if we have good cryptography, then this should be hard. Roughly intuitively, because there are too many possibilities for such a trapdoor. So, so hopefully you cannot try all of them, because this would take too much resources, would take too much time. The second attack strategy would be to try to find the credit card number that's somehow transmitted, to find it right away and try to learn something from this message that was sent here. And if the cryptography is good, then this should be hard too. But so the point here is that if I have a lot of resources, I could try out all the possibilities, and I could actually recover the trapdoor, and I could actually find the secret information that was transmitted from my device to the server. So I need this problem to recover the trapdoor to be very, 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 very hard. So what I would like to do is, I would like to show you some hard problems. And one problem that is actually used in HTTPS is factoring of numbers. And factoring of numbers means you have a number P and a number Q, you multiply them. This is a prime, and this is a prime. And then we have our little adversary. And the adversary gets n and tries to find P and Q. And so this is a problem if these prime numbers are 2 and 3, then this number is 6, and probably then we can just try this out. But if these prime numbers are very large, then it's believed that it's very hard to recover these prime numbers from this number n. But so factoring is believed to be hard. Who tried to factor numbers? Who in the audience has personal experience with factoring numbers? Very good. Yes. I also, yeah, good, very good. You also tried. Okay, I also spent a sleepless night trying to factor numbers. I think the most cryptographers try this at some point. So the issue with factoring is that to explain which type of hard problems we use, I would prefer to relate to something that hopefully you have you can relate a little bit better to, which are sudokus. And so here I'm So here I'm very inspired by this paper by Russell and Pagliazzo called A Personal View of Average Case Complexity. So it's a very nice story that does not involve dragons, but is still is nice, very nevertheless. Okay, so there is an anecdote about the mathematician Carl Friedrich Gauss when he was still very small and in primary school. So back then, so this is let me draw a picture, very accurate picture of Carl Friedrich Gauss in primary school. And so Carl Friedrich Gauss had this teacher called Professor Gruss. And Professor Gruss was very intimidated by having a very good student and tried to embarrass Gauss by giving problems to Gauss that Gauss cannot solve. Yeah, and so one of the famous ones that Professor Gruss gave to Gauss was, okay. So now you're going to add all the numbers from 1 to 100. And okay, so Gauss, I don't know how Gauss approached this, but probably he looked at it for a second, thought like, okay, doing this addition, this would be very boring and take a lot of time, and then maybe he started to kind of to write write up all those numbers, or maybe some of them. And then you figured out, okay, so if I add this, the first number and the last number, this gives 101. If I add the second number and the penultimate number, this also gives 101. And if I add those two, this gives also 101. And then, okay, so how many pairs are there? Okay, right, so I match, so I have 100 numbers, I match each number and they will meet at 50 and 51. So I have 50 of those numbers. So very easy. 5050. Gruz, of course, he did not know all of this was happening. And now, this is the moment when we realize that this is actually not a good hard problem. Yeah, so because how does Gruz even know that this is the right answer? Gauss could just say anything, right? As long as so this is not a good problem. So firstly, because it's easy to solve, and the solution is hard to verify. Yeah, so this is bad. It would be much better if it were the other way around. Yeah, so if we have a problem that is hard to solve, but once you get a solution, it's easy to verify. So this sounds a bit abstract. So let's be very concrete. How about Professor Gruz giving the following sudoku to Gauss? Okay, so a sudoku is a 9 by 9. It's a 9 by 9 square containing 9 lines and 9 columns. And say you start with a couple of numbers, say 2, 7, 4. And this is probably not readable in the back, but if you're in the front and you want to solve this problem later on, I haven't tried it myself, but I heard that this one is very hard. And so, okay, so Professor Gruz could have given this sudoku to Gauss, and so solving this sudoku means to complete these fields with a number between 9 and 10, such that each line has each number from 1 to 9 exactly once. Each column has each number from 9 to 1, from 1 to 9 exactly once, and each of these little boxes has each number from 9 to 1 exactly 1. And so sudokus. So who has tried to solve a sudoku before? Very good. Okay. So hopefully we all have good experience in knowing that the sudokus are hard. But when someone shows us a solution, then we see, oh yeah, clear. This is right? So if someone completes them, then we can easily verify it's the correct solution. And so in the kind of so for computers, a 9 by 9 grid is not so hard because a computer can try out all the possibilities. But if you take a 16 by 16 grid or a 25 by 25 grid, if you scale this up a little bit, then there are sudokus that we think are very, very hard for computers, and so for those of you who have heard of the P versus NP question, So the question whether there exist problems that are hard to solve but easy to verify, this is the B versus NP question. And this is a foundational problem of theoretical computer science, which has been translated into a lot of different areas of mathematics. And if anyone solves it, they get $1 million. Yeah, and it's been open for quite a while. And but kind of we still believe that the sudokus are hard. Right, and I mean, we cannot prove that the kind of scaled up sudokus are hard for computers, but we kind of still think that hard sudokus exist. We can't prove it, but well, actually, even if we could prove it, we would still maybe Professor Gruss would still not be fully happy because he encounters Gauss every morning, right? So every morning, Professor Gruss needs to come up with a new sudoku to keep Gauss busy, and give him a problem that he can't solve. So Professor Gruss, what he would like to have, he would like to have a generator for a random hard sudoku. And this random hard sudoku should it should not be hard kind of every second week. It should be hard every day. Just to go back to cryptography for a second, we want encryption schemes to be kind of not be broken all the time, right? We don't want them to be broken 9 days out of 10, and the 10 days that they're secure. So we want to generate problems that are really, really hard with very high probability. So generating a random hard sudoku is something that we would like to do. But what would be even better for Professor Gruss would be to generate a full sudoku. So a sudoku with all the numbers, and then remove some numbers such that he gets a hard sudoku. Because then Professor Gruss can give this to Gauss, and if Gauss fails to solve the sudoku, he can say, well, but I can solve it, here's the solution. Yeah, so it would give him some possibility to claim that this problem was easy. And it's actually not, but because he started from a solution and then just turned it into a hard problem, he can later claim that he can solve this easily. And so this is this is called a one-way function. In cryptography, and this is a function that is easy to compute in one direction, but hard to compute in the backwards direction. And so maybe a one-way function. This is not yet. So maybe we're thinking about one-way functions is maybe not so exciting because we want to encrypt messages. We want to do much more fancy things. But the thing that we know is that essentially all cryptographic primitives, they imply one-way functions. Yeah, so we don't know whether one-way functions exist, but even more fancy cryptography that we care about more, we also don't know whether it exists because they all imply one-way functions. And so, put the other way around. If there are no one-way functions, I need a new job because all the things that I'm working with, yeah, they are proven not to exist. So you know, when I have this sleepless night worrying whether one-way functions don't exist, then I sometimes think like, okay, maybe I should just you know, just pack some of my colleagues and we go to the mountains for, I don't know, 5 years, 10 years, and we just, you know, we just work very hard. And we prove that one-way functions exist. And then we all come back, and all cryptographers, they will sleep so much better. So, unfortunately, if there are one-way functions, then NP is not equal to P, or put differently, this problem here. It has the feature that it's hard to solve, but the solution is easy to verify, right? So if this problem is hard, then also there exist problems that are easy to solve. Hard to solve, but the solution is easy to verify. So therefore, okay. So if we show that a one-way function exists, great. We also get $1 million. But also we solved a very, very hard problem. And so. To go back to this original setting, where to this original setting, what we had here was that this function was easy to compute in the forward direction, but was hard to revert for an adversary, but it was easy to revert with this additional trapdoor. So below we have even more fancy hard problems where in addition to this hardness of inverting, we have something that is easy to invert with a trapdoor. So that means that Professor Gruss could come up with a sudoku that's very hard for Gauss, but easy for the neighbor of Gauss. Yeah, so the neighbor of Gauss could have a trapdoor for solving the sudoku. But Gauss himself struggles to solve the sudoku. So actually, I do not know how to build a trapdoor function out of sudokus. If anyone has a suggestion, I think I would be very excited. But what our current systems use, what HTTPS uses, is the hardness of factoring to kind of build trapdoor functions. And so many people believe that quantum computers are just around the corner. Quantum computers, they can factor numbers. So we do actually need new trapdoor functions. And there's currently a competition on post-quantum cryptography that tries to build trapdoor functions that will be secure in a post-quantum world. So sudokus are not amongst the candidates, but so there's no sudoku-based crypto used in our real-world systems currently. But also the hardness of sudoku for computers. So hardness of sudokus for humans is fairly well studied, but hardness of sudokus for computers is not so well understood. So I can actually not tell you whether we could build good cryptography based on sudokus. But yes, so one of the very hard things would be to embed a trapdoor into a sampling algorithm for a sudoku. So so we don't know whether there are problems that are easy to solve. sorry, they don't know whether problems that are hard to solve, but the solution is easy to verify. We believe it's true. We also believe that we can sample hard problems. We even believe that one-way functions exist, and we even believe that trapdoor functions exist. But we cannot prove any of those things, and we need to study each problem individually. And when you read the statement, a protocol was proven secure, or this application is provably secure, what this means is that it is based on very well-studied assumptions, like unlike sudokus, but assumptions that we really understand well. And one of the kind of the more fancy cryptographic primitives are those trapdoor functions. I would like to show you another application of trapdoor functions. So this is a children's toy. Careful, it snaps. Yeah. Can you press a tooth? Okay. So this is a children's game where okay, so one of the teeth is forbidden, and at some point the crocodile will snap. Oh, you're fine. Okay, which one was it? This one. Okay. So, you want to try another one? Okay. So this game is of course best if this crocodile does not choose the same tooth all the time. Aha, this one? Yeah, this one. Okay. Oops. Oh, it's getting okay. Yeah. Okay. Okay. So the crocodile chooses a different tooth each time, and so of course this crocodile can't roll dice. It cannot actually choose a random tooth each time. It can only choose something that looks random, that is pseudorandom. And so pseudorandom generators, they are used in our systems to generate randomness for cryptography. And one thing that would be very bad for a pseudorandom generator is if the pseudorandom generator has a backdoor. So you can actually predict the next tooth. So I don't know which one it was. Was this one the last one? So let's assume I have a backdoor. Well, okay, maybe my backdoor is not that good. Yeah, I think my backdoor is very bad. Anyway, okay. So, but let's say I have a backdoor now. Well, okay. Well, okay. So maybe my backdoor fails from time to time, but if I can get 2/3 out of all the keys that are around in the world, then this would already be pretty effective for decrypting information that is around, and this is actually. This is actually something that happened. So there was a pseudorandom generator that was standardized and deployed in many real-world systems, and the NSA sneaked when this was standardized, the NSA sneaked in a proposal that was where they knew a vector and they could actually predict these numbers. Yes, I mean, for such a crocodile, this might at most annoy your children if you always win, but for a real world pseudorandom generator, we really want that there is no backdoor or no trapdoor, which is essentially the same thing, just that we call it trapdoor when it's something that we want, and we call it vector when it's something that we don't want. And so coming up with good trapdoor functions is already quite a non-trivial task. But also showing that the pseudorandom generator does actually not have a backdoor, this is also very hard. And we don't know how to do this. So I hope you got a rough idea of the type of hard problems that you try to come up with. I hope we're soon going to have our first encryption scheme based on sudokus. Yeah, thanks.
Much, Chris.